Good evening and welcome to part 2 for nuclear reactions, and this is for level 3 physics for the level 3 modern physics internal standard with 3 credits, or it can also be tested at the end of the year in the scholarship exam. So first thing we're going to cover is neutron versus proton in the nucleus. So when the nuclei is small, the requirement for a stable nucleus is roughly the number of neutrons is equal to the number of protons. So for a stable nuclei, for small nuclei, the number of neutrons is roughly equal to the number of protons. So for example, for oxygen, it has a mass number of 16, and an atomic number of 8. Therefore, there are 8 protons and 8 neutrons that are equal, and therefore, for small nuclei, this is roughly the optimal number. As the nucleus is getting bigger, more neutrons are needed than protons in order for a stable nucleus. Hence, there are more protons than neutrons. Sorry, there are more neutrons than protons, wrong way around, sorry. Hence, there are more neutrons than protons in a stable, larger nucleus. So the following graph shows the relationship between the proton and the neutron number in the nucleus. As we can see here, the solid black line is representing the black solid line is representing where the number of neutrons is equal to the number of protons. But as you can see here, for small nuclei, it's roughly that the number of neutrons is equal to a proton. It follows the line. However, for larger nuclei, as you can see, the number of neutrons is actually bigger than the number of protons. Alright, first type of decay we're going to cover is beta decay. So beta decay occurs when a nucleus turns into a proton and an electron, as well as an antineutrino. The electron is then ejected from the nucleus. So beta decay occurs when the ratio of neutrons to protons is too high. So as you can see here, when a nucleus turns to a proton and electron, it's actually not actually nucleus, it's a neutron, sorry. Beta decay occurs when a neutron turns to a proton and an electron. So a neutron is a nucleon and a proton is also a nucleon. So the nucleon number doesn't change. However, due to this decay, the number of neutrons decreases by 1 and the number of protons increases by 1. So the purpose of this is because in certain nucleus, the number of neutrons are too high. And therefore, in order to solve this problem, some of the neutrons will become a proton and electron and eject the electron by beta decay. So the number of protons will increase by 1 and the number of neutrons will decrease by 1. The energy released in this decay will be shared between the particles formed in the decay. However, the energy that's expected to go to the electron is shared between the electron and antineutrino. So in terms of antineutrino, all you need to know is that it's a subatomic particle that is massless and has no charge. And it's just that some of the energy that's expected that would be going to the electron, so that the electron would have, or some of it will actually go to this antineutrino, which is actually just a massless subatomic particle, and which also has no charge. So a common example of beta decay, so this is beta decay of strontium, and that is strontium decays into yttrium. So that's when the one electron is ejected as well as the antineutrino. Alright, so gamma radiation. Gamma radiation does not affect the number of nucleons, neutrons, or protons in the nucleus. As we've seen in the beta decay, beta decay actually affects the number of neutrons and protons. Number of neutrons decreases by 1, number of protons increases by 1. However, gamma radiation does not affect the number of nucleons, neutrons, or protons. Gamma radiation can actually occur after an alpha or beta decay. When after the decay, the resulting nucleus is in an excited state, quote unquote, and it returns to its ground state, so it returns back to its resting state by emitting a high frequency radiation or a gamma radiation. Okay, so this can be just gamma radiations. It can be in the high frequency photons. For example, for cobalt-60 is a source of gamma radiation. After it undergoes beta decay to nickel, only about 1/6 of the energy is released in the beta decay. So the rest of the energy is released in the form of the gamma radiation. So because nickel is in an excited state, since only 1/6 of the energy is released, nickel is in an excited state, which allows it to emit gamma rays, 2 sets of gamma rays, to return to its ground state. So E equals to mc squared can be used to calculate the energy it can be used to calculate the frequency of the rays given the energy, or you can use the frequency to calculate the energy of the rays. And you can actually use this to also find the energy of the photon or the frequency of the photon of the rays. Alright, so alpha decay. So very large nucleus are often unstable as the nuclear strong force that holds the nucleus together becomes weaker at larger distances. So alpha decay occurs when a helium nucleus, so that's 2 protons and 2 neutrons, which are tightly bound together, are separated from the original nucleus. Since there is a change in the number of protons, the element will change as well. So that's actually the same with the beta decay as well. Since the number of protons has changed, the element will actually change as well. So in this case, in alpha decay, 2 neutrons and 2 protons are emitted. Therefore, the proton number has changed, the atomic number has changed. Therefore, the element will also change as well. So alpha decay can usually be treated as a simple explosion. So we can actually use conservation of momentum, and so by using conservation of momentum, the speed of the nucleus and alpha particle can be found. The speed and the amount of energy they have can also be found. A common example of alpha decay in this case, so Americium can actually undergo alpha decay to become Neptunium as well as an alpha particle. Right. Right, so in this case, okay, so Americium nucleus will emit an alpha particle that's 2 protons and 2 neutrons, and the resulting products would be the Neptunium nucleus, mass number 237 and atomic number 93, as well as the alpha particle. Alright, so writing nuclear reactions given the word equation. Okay, so for example, an atom of francium Fr, atomic number 87, mass number 223, is formed when actinium Ac undergoes an alpha decay. Write an equation that represents this reaction. So I want you to give this question a go, and when you're ready, keep watching the video to find out the answer. Right, so in this case, we have an actinium that undergoes an alpha decay, so it's going to emit a helium nucleus that's 2 protons and 2 neutrons. So we know that the resulting product is francium nucleus, which is atomic number 87, mass number 223. Therefore, the original product, actinium, must have 2 more protons and 2 more neutrons than francium, because francium is a product after an alpha particle is emitted. So therefore, we have our actinium must be mass number 227 and atomic number 89. That undergoes alpha decay to become 223 mass number and atomic number 87 francium element. Part B, francium that undergoes a beta decay to form the radium nucleus. Write a nuclear reaction that represents this change. So I want you to give this question a go, and when you're ready, keep watching the video to find out the answer. Right, so in this case, francium undergoes a beta decay. So once again, we covered that the neutron becomes a proton and an electron, and then the electron is emitted from the nucleus. Okay, so once the electron is emitted from the nucleus, okay, we'll have one less neutron and 1 more proton. So therefore, we know francium has a mass number 223, atomic number is 87. Therefore, in order to undergo beta decay, all we need to do is we need to add 1 to our atomic number, and our mass number stays the same because our total number of nucleons has not changed. The total number of nucleons is not changed because one neutron has decayed to a proton and an electron. A proton is still a nucleon, okay? So 1 nucleon technically has become another nucleon, so therefore there's no change in the mass number. So in this case, we'll have 223, mass number 223, and atomic number 87, francium, undergoes beta decay in order to form our radium nucleus, as well as emitting the electron, so as well as the anti-neutrino. So anti-neutrino is just a V. It's just a V, but in this case, because Microsoft Word, when I'm writing these equations on Microsoft Word, they don't give me the option to put the line on top of the V, but there's actually a little dash on top of the V to indicate the anti-neutrino. So just remember, above the V there is a small line, small dash above the V, and that's to represent the anti-neutrino. Alright, so moving on to scholarship concepts. So that's conservation of momentum. Very, very common scholarship question. So in this case, the question so during usually asks about so during an alpha decay, it usually asks us how much of the energy is given to the alpha particle and how much of the kinetic energy is given to the nucleus. Okay, very common scholarship question. So during a decay, momentum is always conserved because there are no external forces acting on the system. In scholarship questions, this is commonly applied to the alpha decay. So the question will usually ask what percentage of the kinetic energy would be distributed to the alpha particle and how much of the energy would be distributed to the original nucleus. Assuming the nucleus is originally stationary, in order for momentum to be conserved, this means that the nucleus and the alpha particle must be moving in opposite directions after the explosion. Okay, so because the original momentum is 0, and we know that the momentum of the center of mass is therefore 0, that means the overall momentum of the center of mass after the collision has to also be 0. So therefore, the vector addition after the explosion must be 0. So therefore, they must be moving in opposite directions in order for the momentum to cancel out, the vectors to cancel out, to get an overall 0 momentum. Okay, so they have to be moving in opposite directions. In this case, for example, we have our original nucleus, that's our momentum equals to 0. And then after, we're going to have our alpha particle, which is a small dot here. That's going to have a larger velocity because it's lighter, and it's going to be moving into the opposite direction as the nucleus, which has a smaller velocity because it's heavier. Alright, so here's an example question with americium. So an americium nucleus is at rest and it decays into a neptunium-237 nucleus by an alpha particle. The products fly in opposite directions, so determine the percentage of EK taken by the alpha particle. Determine the percentage of EK taken by the alpha particle. So I want you to give this question a try. Sorry. Part A. Okay, first I want you to do part A. So write a nuclear reaction for this decay. So I want you to give this question a try, and when you're ready, keep watching the video to find out the answer. Alright, for this question, it's simply just americium. So we know that alpha particle is simply a helium nucleus with 2 protons and 2 neutrons. Therefore, we're going to add 4 to our mass number, and adding 2 to the atomic number of neptunium will give us back to our americium. So americium will have a mass number of 241 and a atomic number of would be they will give you the periodic table for this one, so I can't really remember which one or what cannot remember what the what the atomic number is, but for the exam they'll give you the periodic table of elements, so you should be able to find the elements on there. So the correct answer in this case is, so neptunium is atomic number 93, so we just need to add 2, will give us atomic number 95 for americium, as well as the alpha particle. Question B. Assuming the mass number is approximately equal to its mass atomic unit, so that's the mass, so determine the percentage of EK taken by the alpha particle. So basically assuming that for the alpha particle the mass number is 4, so therefore its mass is 4 mass atomic units, and for neptunium its mass number is 237, so assume that its mass is 237 atomic mass units. Alright, so I want to give this question a try, and when you're ready, keep watching the video to find out the answer. Alright, so here we need to actually undergo some formal derivation. So we know that P equals to mv, and we know that the kinetic energy of neptunium equals to half the mass of neptunium times the velocity squared of neptunium. Likewise, the kinetic energy of the alpha particle will be equal to half its mass times half its velocity. We know that momentum is conserved, and since they're moving in opposite directions, their momentums will be the same but in opposite directions. Therefore, therefore the magnitude of their momentum will be the same. Therefore, the mass of the alpha particle times its velocity equals to the mass of the neptunium nucleus times its velocity. We know that mass of neptunium equals to 237 over 4 times the mass of the alpha particle, and that's because we know that the mass of neptunium is 237 atomic mass units, and the mass of the alpha particle is only 4 atomic mass units. So we know that 237 over 4 times of 4 will give us the mass of neptunium. Therefore, 237 over 4 times the mass of the alpha particle will give us the mass of neptunium. So therefore, if we plug those numbers into our momentum, we'll see that the mass of the alpha particle will actually cancel out, and it will give us that the velocity of the alpha particle equals to 237 over 4 times the velocity of the Neptunium nucleus. Sorry. Alright, so if we plug these numbers in, so we plug in that mass of Neptunium is equal to 237 over 4 times mass of the alpha particle, and we substitute that the velocity of the Neptunium nucleus is equal to 4 over 237 times the velocity of the alpha particle. We'll get that the kinetic energy of the Neptunium nucleus is equal to half times 237 over 4 mass of the times mass of the alpha particle times 4 over 237 squared times velocity squared of the alpha particle. We know that the kinetic energy of the alpha particle is simply equal to half its mass times its velocity squared. And we know that after simplifying this equation, we'll get that the kinetic energy of Neptunium is equal to 2 over 237 times its the mass of the alpha particle times the square of the alpha particle speed. The percentage of the kinetic energy that goes to Neptunium is simply the total energy of the Neptunium nucleus divided by the total energy of the system. So in this case, the mass of the alpha particle and the velocity squared of the alpha particle will cancel out. So therefore, we're just left with 2 over 237 is divided by 1 over 2 plus 2 over 227, which is the total kinetic energy. And that will give us the answer of 4 over 241. So in this case, Neptunium will take 4 out of 241, which is 1.66% of the total EK. And the alpha particle will therefore take 237 over 241, which is 98.34% of the total EK. Right, I hope that makes sense. And that's all I have for this video. I hope you enjoyed this video on modern physics for nuclear reactions. And if you did, please drop me a like and please subscribe to my channel. And I hope to see you all in the next one. Thank you. Bye.